Okay, so we're going to talk about the instantaneous rate of change, also known as the derivative. So this introduces the next big topic in calculus. So the first big topic is limits, which we just covered. And now we're using those limits to help us jump into the next big topic of calculus, which is the derivative, all right? The last big topic we'll talk about in Calculus 1 are integrals, where derivatives and integrals are related to each other through the limit, which we learned about in Chapter 1. Okay, so let's jump right into this. So in algebra, we can find the slope of a line. No big deal, right? Hopefully. So slope is m equals what? Slope is the change in y divided by the change in x. You might have heard it as the rise divided by the run. So the rise divided by the run, that's the slope. And so the formula for that, if you're given 2 points, you can take 2 points, x1, y1, and x2, y2, and you do the difference in the y's divided by the difference in the x's. Okay? So slope of a secant line is the average rate of change. So this, we're going to introduce the derivative starting out with a secant line, okay? Because right now, without calculus, the best thing we can do is we can find the average. So how do we do this? So say I have some function. So maybe this function here represents the distance we are from home. All right, so maybe this person's like, 5 miles away from home here, then they're only 2 miles away from home, and then way up here they're like 20 miles away from home, whatever, okay? So that f function represents, the output is how far away we are from home. Okay, so how do I find the average rate of change over some given interval? So say I have 2 points, x1 and y1. To get the slope, I literally draw a line through those 2 points, and then I make a right triangle. I figure out the vertical distance, the y displacement. I figure out the horizontal distance, the x displacement there. And now I have those two values. Well, I take the rise divided by the run of those two values there, okay? To find the vertical distance, I always subtract the larger value, y value, from the smaller y value. And then I'm going to continue with the same pattern. If I'm trying to find horizontal distance, I always subtract the most distant, the largest one minus the smaller one, right? So the furthest right minus the left. Okay. So these points on the graph, if I plug in a into my function, I get f of a. If I plug in b, I get f of b. So what do I want to do? I want to find the line, the slope here. Why do I want to find the slope? That's going to represent the average rate of change. This line here is known as the secant line. This red line is a secant line. Okay, secant line cuts through the graph in more than one place. Okay, so you can see that it cuts to the graph in 2 places here. All right, now, the way to think about an average rate of change would be in this sentence here. Think about we're traveling from Lufkin to Nacogdoches. So a car travels at 55 miles per hour on average from Lufkin to Nacogdoches. Now, maybe it's 75 the whole, on the outside of Lufkin to Nacogdoches, but you got to stop at a couple of red lights between Angelina College and the other side of Lufkin, right? So that kind of slows your total average speed down. So this is the 55 miles per hour on average. Now, that's not too hard to calculate, right? We calculate the displacement, right? Divided by how long it took us to get there, okay? So the slope of the tangent line is, that should say is right there, the instantaneous rate of change, okay? So the slope of the tangent line is the instantaneous rate of change. How is this different than the average rate of change? That might be the question there. Okay, how does that differ? Well, say I have some given point C right here that I want to know how fast was I traveling at that instant in time. No average, just that exact moment in time. How fast was my speedometer reading? Okay, that's the question. And this is what calculus allows us to answer with the derivative, okay, the instantaneous rate of change. And so the question that can be answered is the car is traveling 62 miles per hour as we maybe pass the speed limit sign, the city limit sign coming into NAC, okay? So that's a very different question than, what was the average speed over the whole trip? This was, how fast were you going right whenever you passed the city limit sign coming into NAC, okay? So very, very useful there. And up to this point, without calculus, we could not answer this. All we could do was approximate. So what is the big idea here? How do we jump from the secant line to the tangent line, where the tangent line only touches the graph in one spot versus a secant line, which needs two spots to touch the graph in order to get your slope? You need 2 points, right? Okay? Because if you only have 1 point and you're trying to find the slope, well, what happens? You get y. Let me write this in something you can see. If you only have 1 point where you're touching it, like that's c comma f of c, right? Well, it would be like this. It would be, okay, f of c minus f of c over c minus c. Well, guess what? That's 0 over 0, which we talked about that in the last chapter. That's an indeterminate form, okay? So it's of no use to us to find the exact, because without two different points to choose from, our average formula for slope rate of change falls apart. Okay, so we've got to have 2 points for that to work. So this is why calculus is important to us. So what is the big idea here? What is the big idea? Well, say I have some curve, okay? So what I want to do is start with the slope of the secant line. So let's pick 2 points. I'm going to let x be arbitrary, and then have my x naught here, okay? And I want to find the slope through those 2 points right there. So I have to go back to my slope formula. Now, I need to know what the outputs are, what these 2 points are. Those 2 points are this right here is x naught comma f of x naught. And then this point here is x comma f of x, right? So I take, for a slope, I do y2 minus y1 over x2 minus x1. So y2 minus y1, that gives me the numerator. And then I divide by x2 minus x1, okay? So I'm going to write this in here. Okay, so that's where this comes from. The definition here for slope, that's how we're figuring this out. Okay, of these 2 points right here. So the secant line has a slope. Now, I want to make a clever substitution here. Now, instead of representing this as an x and an x naught, I'm going to call this distance between x and x naught, I'm going to call that distance h, okay? So how do I find the distance between x and x naught? I take the right minus the left, so I do x naught minus x, okay? And so now that I have this substitution right here, h equals x naught minus x, I'm going to substitute x naught for something in terms of x and h. Well, how do I solve for x naught here? I'm going to subtract, or I'm going to add x to both sides, and I get x plus h equals x naught. So everywhere I see an x naught, I'm going to put an x plus h here. I'm going to substitute. That's what I'm doing. Okay? So I make the substitution, and now the thing that's useful about this is I have x plus h minus x in the denominator, and guess what? X minus x cancels, and so I'm only left with h in the denominator. So I have this formula for the secant line, which is known as the difference quotient. Okay, so this has a special name. It's called the difference quotient, right? So it tells us the slope of the secant line between 2 points that are a horizontal distance h apart from each other. So what happens? What happens? How do I go from a tangent line to from a secant line to a tangent line, right? How do I make this secant line turn into a tangent line? Well, what I'm going to do is I'm going to take a limit as h goes to 0. So what do I mean by that? I'm going to shrink my h value. So I'm going to pick x naught values that are closer and closer and closer to my x. And as I do that, my h, my distance between x and x naught, is shrinking to 0. So that's where the limit comes into play here, and why we had to introduce limits before we could a derivative. So that's a smaller h here. So I pick points that are closer and closer and closer. What's happening? My secant lines are getting closer and closer and closer. As you can see, they're getting closer and closer to my true instantaneous rate of change. And then finally to the point where I reach that indeterminate 0 divided by 0 form there. Okay? That's as h limits to 0. Okay? So I'm going to show this in a faster... Uh-oh. Okay. All right. So as h goes to 0, the secant line gets closer and closer to the tangent line. That's the idea. Okay, I like to use color a lot here. This blue means something that represents, it lines up with that blue tangent line right there. Okay, so as my h heads towards 0, the secant lines get closer and closer and closer until they become the tangent line. Okay, that's the idea there. I'm going for the goal of the tangent line right there. So I take the limit as h goes to 0 of this difference quotient. Now, the definition of the derivative, okay? So the definition of the derivative, let f be a differentiable function on an open interval. Then the derivative of f of x, which is read f prime of x. Okay, we read this as f prime of x. So that's f prime of x is equal to, what is it equal to? The limit as h goes to 0 of the difference quotient right here. Okay, so that's why I wanted to show you that substitution, so it's not like, well, where in the world did that come from? Okay, I want you to understand where these pieces came from, right? This is the derivative of f. Okay, now there are several notations here, and you were expected to know each of these notations. So all of these represent the derivative of f. F prime of x, y prime, dy dx, that's like the change in y divided by the change in x that we talked about at the very beginning when we talked about algebra slope, dy dx. D is for delta. This is the Greek letter for the capital delta, change in x, okay? Df dx, which is the derivative. I read this as the derivative of f with respect to x. The next one is the derivative with respect to x of the function f. And then this one is the derivative with respect to x of y. This dx in the denominator, also known as the differential, this tells us what to take the derivative with respect to, okay? So this little thing in the denominator tells us we're taking the derivative with respect to x. Okay, so I would read this, the derivative of y with respect to x, dy dx, okay? Y prime, f prime of x, okay? So just a lot of little different things there. You could also just say f prime too, a little bit less formal. It's a little more informal, but it'll work too as long as you don't need that x in there for some reason. Okay, guys, so hopefully you understand the big idea here. We're literally in calculus, what we're doing here is we're taking something that we know how to do from algebra, and then we're using a limit in some way to get this indeterminate form where then we can say, okay, if I limit h to 0, then that means I can get to as close to the same 2 points as possible. And when I'm taking the idea of limits, I'm actually able to push it beyond and say this is the instantaneous rate of change. Okay, so very, very powerful stuff. All right, guys, so that's an introduction into